Swayam Prabha. Digital India. Educated India.
Welcome back. So let's continue the discussion on the laminar diffusion flame. So we have done our discussion on the jet flows and then the jet diffusion flame which is reacting. Now we start some basic jet diffusion flame. First we look at the some historical aspect of it and when it was initially described. So, I mean then that time people were trying to establish the theoretical description of this kind of flames. So, one was the or which is very well known in the laminar diffusion flame is the Bach-Schumann kind of flame which was in 1928. So, where the assumption is that constant velocity field parallel to the flame axis, where the reasonable prediction of flame height for round burners. So, these are the output of that. Then 1977 Roper and Roper, they did a relaxed single constant velocity assumption. This provided a extremely good prediction and their data was also quite matched for by the with the experimental observation of the results, and this was valid for round and slot burners. So, these are the historical aspect. Now, we can look at these some of these solutions. One is this Roper's solution and correlations. Okay. So, we take an circular port. Then the flame height is correlated with volumetric flow rate Tf 4 pi 1 plus 1 by s T infinity by Tf 0.67. Now, LF experimentally observed that 1330 1 plus 1 by s. So, there is a quite nice correlation. Here S is the stoichiometric molar oxidizer fuel ratio, stoichiometric molar oxidizer fuel ratio. Okay. And then we have d infinity, which is obviously the mean diffusion coefficient of oxidizer. This is the mean diffusion coefficient of oxidizer at T infinity. Tf and Tf are fuel stream and mean flame temperature. So, this is fuel temperature, this is flame temperature. So, this is how the correlation provided by these people. Now, if the instead of a circular port, if you take an square port, then we get a different expression from the flame height, which is QF (16 D infinity (1 plus S) T infinity by T f. And the experimentally observed lift off height was 1045 QF TF inverse 1 plus S which is now this inverse function is inverse error function, which is defined as ERF W is 2 by root pi 0 to W dt. So, this is how the inverse function is defined. Now, if the slot burner is momentum controlled, then the correlation is different, and it was given that. So, these correlations are also available in any standard book, because these are well established correlation proposed long time back. So, one can find that out, which is T infinity by point. Now, experimentally what is observed is that beta which is T infinity by, here B is the slot width, H is the length, and beta is 1 by 4 into inverse F 1 by 1 plus S. This is what it is. Now, if we define I, which is the ratio of the initial momentum flow to that, to the slot, to the uniform flow, that is how you get. Now, for uniform flow, I would be 1, and fully developed flow, if we assume it is a parabolic which is fully developed, this I would be 1.5. Now, this is where the correlation that we looked at, that when the slot burner is momentum control. Now, there could be another situation where this slot burner is buoyancy control. in that case the lift off height of the flame is different, and that is given as 9 beta to the power 4 QF to the power 4 T infinity to the power 4 square AH4, which is 1/3. And experimentally observed this thing is beta 4 QF 4 T infinity 4 by so which is 1/3. Now here there is one more nomenclature A, which is your mean buoyant acceleration, that is Tf by T infinity minus 1, and G is as usual gravitational acceleration. So every situation, even if you take a slot burner, whether it is a momentum control or buoyancy control, the expression of the flame height is different. Now we look at the slot burner where it is in transition regime. That means we look at this slot burner in transition regime. Now then one parameter which becomes important to define is the Froude number, which is V I YF Now what it does, physically this Froude number represent the ratio of the initial jet momentum flow to the buoyant forces, which is experienced by the flame. So this is initial jet momentum flow to buoyant force experienced by flame. So that is the ratio. So there could be situation where this is very much higher than 1. So this is a special case. If this is very higher than 1, that means buoyant force effect is less. So it is more or less the jet momentum. So this becomes a momentum control situation. Momentum control situation. Now if FRF is 1, this is the transition. Or mixed, that means, and the other possibility is that FRF less than 1. So if it is less than 1, momentum is not that much, so it is essentially buoyancy controlled. Now one can note that LF must be known a priori to establish the appropriate regime. So it essentially in sort of trial and error approach, because LF to be known a priori. So, this is little bit trial and error approach. Now, we can take a situation where FRF is of order of 1, then my LFT is 4 by 9, LFB one plus LFN so that is how you get in the situation. So, depending on the Froude number and all these things you can get. Now, these are pretty much the about jet diffusion flame what you can have. Now, what happens in the diffusion flame, you get soot, which is one of the problem in the jet diffusion flame. You get soot formed and in the jet diffusion flame. So, why that happens? There are some factors like fuel type. So, it depends on the, when you talk about the fuel type, it is primarily soot happens when you get these hydrocarbon fuels. When you burn the hydrocarbon fuel, you get these soot particles. These are black particles that you get. Now, it depends on fuel type. So, what you mean by the fuel type is that it is the essentially the chemical structure and composition. Then dilution, that is another issue. So, it can tell you whether it is inert or reactive dilute. Then the underlying flow field, which is another important thing, that is your turbulence. So, the time scales and all these things would be important, because now once your flow field is turbulent, it has different time scale compared to chemical time scale. Then obviously your temperature, pressure, these are factors what impact that. So, typically this is a problem in your premixed flame. This is not a problem in premixed flame. Premixed flame you do not get this unless phi greater than equals to phi critical. So, this is a typical problem you see or it exists in diffusion flame, and there are details which are available, details regarding the soot formation, and it happens because of the conversion of the hydrocarbon fuel with molecules containing a few carbon atoms into carbonaceous agglomerate containing some millions of carbon atoms in few milliseconds. So, in a nutshell you get some carbon particles at the end of the combustion process, which is by nature, and also there is a transition which takes place from a gaseous to solid phase. Now, typically the smallest size of these particles are about 1.5 nanometer in dia, which is about 2000 AMU. So, that means they are such a small particle which are actually formed hydrocarbon fuel combustion. Now, if you look at the soot formation, it actually soot involves, soot formation rather involves a series of chemical and physical processes. So, number 1, there is a formation and growth of large aromatic hydrocarbon molecules leading to soot inception. So, that is probably the first stage or first step towards the soot formation one can think about, where the formation and growth of large aromatic hydrocarbon molecules. So, this is called the soot inception. So, that means this is the transition to first solid particle. So, this is the first transition, that is to solid particle. Then surface growth and coagulation of primary particles to agglomerates. So, that means this surface growth takes place, then they coagulate with each other and there is a agglomeration. Now, thirdly, there will be growth. So, the growth of agglomerates by picking up growth components from the gas phase. Then finally, the oxidation process of agglomerates. So, these are the multiple steps that soot formation actually occurs, and what it happens initially, though, when these higher order hydrocarbons are burnt, they form like an sheet kind of structure, lower order hydrocarbon and sheet like an structure. This is the aromatic hydrocarbon molecules leading to a soot inception. This is called the inception. Then they grow and coagulate and they form like an particle like structure where the phase change takes place, and then the surface growth process, and finally these agglomerates are actually grow, and if it gets oxidized then you do not get to see this, but if does not oxidize then end of that process you get these small particles. Now, the smoke point is that, so there is an ASTM standard which is available to determine the sooting tendency of a liquid fuel. So, that means every liquid fuel one can actually characterize based on this available ASTM standard. Now, this fuel flow rate is increased until the smoke starts being emitted from the flame tip of a laminar flame on a standard burner. So, it is a simple burner where you have a laminar flame, and unless the smoke starts to emit, is the fuel flow rate is increased. So, greater the fuel flow rate, the lower is the sooting propensity. So, generally it is used for aviation fuel specification and dependent on the chemical composition also. Now, this is what one can see pictorially or pictorially that what happens. So, this is at the first step, the pyrolysis process of the fuel. So, this is you get the radical, the lower order hydrocarbon you get. Then from the lower order hydrocarbon, and this happens when you burn the higher order hydrocarbon. So, you get this vinyl radical, then butadiene radicals, vinyl acetylene, all these are formed. Then there is a exchange of bond or breakage of bond that takes place, and then you get to a situation where this kind of structures which you get, the aromatic rings. So, essentially this is the stage where you can think about there is a formation of aromatic structure, or rather I would say that all these intermediate state finally you come to this formation of this aromatic structure, which is a sheet like aromatic structure. This is a sheet like aromatic structure. So, that forms, and then from there first the phase change takes place, and this is the step where you call it a shoot inception. Now, then you have a surface growth, that means these small particles grow. This is what the surface of these assumably spherical particles they grow, and you get the larger size particles. Now, once you get the larger size particles, now at this stage these particles may actually coagulate with each other. If they stick to each other, then you can see a chunk of particles, they stick to each other, and then there would be some agglomeration of this particle. This is a coagulation process, and then finally at this convex downstream it gets oxidized, presence of the OH and these things. Now, if that oxidation, the amount which is formed and the oxidation is balancing out, then there will be no shoot at the end of this process. But if that does not happen, there is a imbalance. So, you get to see end of these black particles. This is the whole thing, the process one can think about. This is a simple example which one can take. There is a fuel tube of this millimeter diameter, this is the fuel flow rate, this is the air nozzle of this millimeter, flow rate of this, visible flame height at 67 millimeters. That means, this is the roughly 67 mm, and fuel is C2H4. Now, this is what happens when you have C2H4. Actually, this fuel comes here, air comes here, and you get the soot particle formation. So, what it does, if the air comes, so there will be a diffusion process, and this is your luminous flame zone, and this portion is your oxidation process. Okay. And these are the particle structure. So, this example we will discuss in more details in the next lecture. We will stop here today.